Hello and welcome to another Common Core Geometry video by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson number 6 on Radian Measure. This is a brand new topic for most of you, and if you've actually seen it before, that's pretty impressive. So let's kind of hop right into it. Without giving you too much introduction, we'll kind of get into that as we go. So we are used to measuring angles. We've been measuring angles since elementary school, right? And measuring an angle is the same thing as measuring a rotation, i.e. how many degrees does it take to rotate one of these rays into the other one. So let's start with a very simple question. Which one of these angles is larger? Which one of these angles is larger? And I know this isn't the first problem on your worksheet or anything, but for a lot of people, they might look at this and go, well, that angle is larger. And yet, if I take my protractor, right, and I do something like this, what I see is that this angle is 30 degrees, right? On the other hand, if I bring this over to here and I measure this angle, I find that it's also 30 degrees. Because the idea of an angle is it has nothing to do with how long the rays are. Rays extend infinitely, right, in those directions. But it's really just all about how much around a circle have we rotated. And the idea is that, right, we've taken a circle, it doesn't matter whether it's really small or quite large. We've taken a circle and we've broken it up into 360 equally spaced distances along its circumference, along its outer side. And now we're just asking ourselves, well, as we move from this ray up to this ray, right, how many of those 360 notches or little distances have we gone? And we're not really particularly bothered by whether the circle is this large or this large, because all circles are what are called similar. Right? All circles are similar. And so, whether the angle is very tiny or whether it's very large, right, the actual measure of the angle ends up being the same in both of these cases. Now, that's important, right? And it serves really as the basis for our being able to measure rotations using circles, right? And that's really what you're using when you use a compass, or I'm sorry, when you use a protractor to measure a rotation. Now, it gets into the idea that all circles are similar, all right? Not all rectangles are similar, all squares are, but all circles are similar, and we're going to start with a little exercise just to remind ourselves what that means. Exercise number 1. Below are circle A with radius R1 and circle B with radius R2. Give a similarity transformation that shows that the two circles are similar. Fully explain why this works. All right, so remember, a similarity transformation, right, is a set of transformations, right? Those could be translations, reflections, rotations, and dilations, which map one figure on top of the other, right? And it must include a dilation. It doesn't necessarily have to include any of the others, but it must include a dilation. So how could we get circle A so that it is mapped on top of circle B? All right, well, let's kind of work through this together. Step 1, right, perhaps we should translate circle A so that point A maps onto point B, right? So in other words, I'm going to take this circle and I'm going to translate it over here. And of course, what that would end up looking like, if I put, let's say, A prime right here, I'm just going to freehand sketch it in, is it would look something like that, right? The two circles now have the same center. Okay, simple enough. Now, how would I want to dilate it? And remember, with dilations, you need two things. You need the center of dilation, and you need a scale factor. Well, think about it for a second. Remember, I want all the points on, I guess now, circle A prime to suddenly be mapped onto circle B. So what should my center of dilation be? Well, it should be that common center. So now I'm going to dilate that was supposed to be a big C, circle A prime, using point B as the center of dilation. But what should my scaling constant be? What should my scaling constant be? So remember, when we dilate something, the center of the dilation doesn't go anywhere, which is good. It's going to keep the center of circle A prime right there. But what should I dilate it by? Well, remember, the scale factor should always sort of be a new length divided by an old length. Right now, all the points on circle A prime are a distance of R1 from that center, but I want them to be a distance of R2 from the center, so I'm going to use point B as the center of dilation and a scaling factor of, remember we typically use K, of R2 divided by R1, right? Okay, and this works because all points now on, I guess it would be circle A double prime, will be a distance of R2 away from point B, right? And that's what we want, because that means it will lie along circle B, right? Essentially, what we're doing, right, is we're moving this circle over to here, and then we're stretching it so that the new radius will be equal to R2, right? Therefore showing that all circles are similar. Now, why is that important? Well, keep in mind that when you have similar figures, the ratios of corresponding parts of similar figures will always be the same. For instance, if I took the circumference of the circle and I divided it by the diameter of a circle, because they're always similar, that number would always have to turn out to be the same, that number being pi, right? And that's kind of a little bit about why pi sort of makes sense, not as 3.14, etc., but why the circumference should always be pi times the diameter. Well, because the circumference divided by the diameter for any circle should remain constant. It's the ratio of corresponding portions of the circle. All right. And that is now going to lead us, right, into the idea of what's known as a radian. All right, and we're going to get there. We're not quite there yet. But let's take a look at the next exercise. Again, based on the fact that ratios of corresponding parts of similar figures will be equal. Let's take a look at exercise 2. Two circles are shown below with sectors defined by central angles of 60 degrees. One has a radius of 5 inches and one has a radius of 8 inches. Calculate the arc length S for both sectors, and then the ratio of arc length to radius. Write all your answers in terms of pi and in simplest form. All right, so let's figure out what that arc length is, what this arc length is. Then what we're going to do is we're going to divide those arc lengths by the radii, and we're going to notice something. So first, right, well, what is the overall circumference of this circle? Right? This is from the last lesson where we were dealing with sectors of circles. Well, the overall circumference, right, pi times the diameter, is 10 pi, right? And the overall circumference of this circle would be 16 pi. All right, that's simple enough. Now, well, what's the arc length then? What is that arc length of this circle? Well, we chose a kind of a nice angle here, 60 degrees. So I'm not going to kind of set up the 60 divided by 360 equals the arc length divided by that, although we could. But ultimately, the arc length, right, should be 1/6 of the total circumference, 10 pi. All right, so that will be 10 pi divided by 6, or 5 pi divided by 3. So that's the arc length along this circle, 5 pi divided by 3. Now the arc length for this one will be 1/6 times 16 pi, right? And that's just going to be 16 pi divided by 6. Again, just reducing. That's going to be 8 pi divided by 3. All right, great, whatever. So that arc length is 5 pi divided by 3. This arc length is 8 pi divided by 3. But the question also asks us to find the ratio of this arc length to its radius. All right, now this is going to be a little bit ugly in terms of division, but just, follow me. I've got 5 pi divided by 3, and I want to divide that by its radius, 5. Over here, I've got 8 pi divided by 3, and I want to divide it by its radius, which is 8. All right? Now, a little bit tricky with fractions, but of course dividing by 5 is the same as multiplying by 1/5. So this is going to be the same as 5 pi divided by 3 times 1/5. Yes? In which case we can do the age-old cross cancellation, and we get a final answer of pi divided by 3. Same thing here. We could have 8 pi divided by 3 times 1/8, and we get pi divided by 3. Now, why did those two come out to be identical? Well, they came out to be identical because just as these two circles are similar, right, these two sectors are also similar, similar sectors, because they have the same angle, right? They're the same rotation. They've got this 60-degree angle. And whenever we divide corresponding portions of similar figures, that S corresponds to this radius corresponds to this radius. Anytime we divide them, we always get the same answer. So it makes sense that it's pi over 3 divided by pi over 3. Right? Notice that the ratio of the arc length to the radius is the same in both cases because the circles are similar and the central angle is the same. All right? But that's kind of interesting because it leads us now to something that is going to feel very, very foreign, which is that we can actually measure the rotation, right, an angle, by looking at the ratio of the arc length to the radius. And in fact, that gives rise to what's called the radian measure of rotation. All right? And again, up to this point in time, you've measured rotations using one and only one method, and that's the degree, right? A degree, and that's it, okay? And you've kind of taken it as fact because you've been doing it for such a long time, right? Oh, well, I put my protractor down, I slap it down, I read how many degrees it is, right? Never probably really questioning why is it 360 degrees, why doesn't the length of the rays matter or anything like that, right? You've just used that. Now we're going to introduce something that's going to feel very strange, which is we're going to say that we can measure an angle, any angle, all right, by simply kind of drawing in a circle just like we do here. I can't even bring this thing up, okay. But the difference now is instead of reading off these little notches, we're going to simply say that angle is going to be this arc length divided by this radius. And it's no longer going to have units of degrees, it's going to have units of radians, all right? Radian angle measurement, all right? Simply defined as the arc length divided by the radius. And again, it probably seems strange, except that here you've got these two 45-degree angles, okay? They're equal rotations. And the idea is, right, if I took that arc length and I divided it by that radius, I'd get exactly the same thing as if I took this arc length divided by this radius. So we're going to use that ratio to actually give kind of an angle answer. It's just that it's not measured in degrees anymore. It's measured as this ratio, okay? And again, this will take years for you to really become comfortable with, especially because it seems like radians must, that it must depend on the size of the circle. So let's first start with something very basic about radians. If we were to rotate all the way around a circle, how many radians would it be? Right? We know if we rotate all the way around a circle, it's 360 degrees. How many radians would it be? Let's take a look at that in this first exercise, really with radians. Exercise number 3. Given a circle whose radius is r, answer the following questions. Letter A. What arc length, s, is traveled in a full 360 degree rotation? Express your answer in terms of pi and the circle's radius. So remember, we've got this whole theta, that's my angle, equals s divided by r. So if we go all the way around a circle rotation, we go all the way around, then what is my arc length all the way around? Well, it's the circle's circumference. And what is the circle's circumference? Well, it's 2 pi times the radius. Right? That's all the way around. All right? 2 pi times the radius. So letter B then says, given that radian measure is always theta equals s divided by r, what radian measure represents a full rotation around a circle? Well, let's just do the calculation. That angle measurement is going to be s divided by r, but all the way around a circle we have 2 pi r divided by r, and what happens is that those radii cancel and we get 2 pi radians in a full rotation. And that's it. So whereas a full rotation is 360 degrees, a full rotation is 2 pi radians, which is about 6. A radian is much larger than a degree in terms of a unit, all right? About 6 radians go all the way around a circle. By the way, if the word radians kind of reminds you of the word radius, that is not a great surprise. In fact, what radians really are is basically saying, look, if I had a circle and I walked along the arc length, how many radii, if I bent them and laid them out along that circle, how many radii have I traveled? All the way around a circle, and you've traveled 2 pi radii around the circle, right? But we call them radians. All right? Still, it's a simple enough formula to use, right? For instance, if I've got this exercise number 4, in the following diagram, 2 sectors are shown with central angles labeled. Which has the greater radian rotation? Which has the greater radian rotation? Note, this isn't drawn to scale. Well, it really is pretty easy. When I take a look at this, if I want to know the radian rotation here, theta sub a, all I need to do is take that arc length, 15, divide it by the radius, 6, and I get some kind of an answer. In this case, it's 2.5. 2.5 radians. Not degrees, it's way more than 2.5 degrees. 2.5 radians. On the other hand here, theta b, well, that's going to be its arc length, 8 divided by its radius, 18 divided by 8. That ends up being 9/4, or 2.25 radians. Sorry, we're just barely fitting that one in. 2.25 radians. So, which one's greater? Theta A is greater. Very, very simple. Rotation measured by the ratio of arc length to radius. Easy, because it's just a division problem, but weird. You're probably looking at this going, no. Rotations are measured in degrees and degrees only, right? This seems more like a calculation than a measurement, and yet it truly, again, is a measurement of rotation, because regardless of how big these 2 circles are, right, that ratio is indicating that this is a greater rotation than this one. All right? me step back, go ahead, take a look, and then we'll keep going. All right. Let's take a look at one more problem. All right, in this particular problem, exercise number 5, we're told a pendulum whose length is 14 inches swings through a central angle of 0.38 radians. What length does its tip move through in a single swing? All right, so in other words, right, we've got this thing, we drop it, and we're told that we've got 14 inches here and that the angle of rotation in radians is 0.38 radians, okay? What we want to know is this distance. We actually want to know an arc length, S. So we've got this formula that just simply says, look, theta is equal to S divided by R. So far, right, if we knew S and we knew R, we were able to calculate theta. This time, we know the rotation, we know the radius, we want the arc length. We want to know the distance that the thing has swung through. Now we could substitute the numbers in right now. We could say, all right, we've got 0.38 is equal to the arc length divided by the radius, right? 0.38 equals S divided by 14. Simple enough now, we can just multiply by 14 on both sides, right? So my arc length is now 0.38 times 14. We want to have our calculator do that for us. I've got the answer already down, 5.32 inches. It's interesting because again, what that thing really represents, that 0.38 radians, is that we've gone 0.38 radii along this arc length, 0.38 radii. So if we want to know how long the arc length is, we literally multiply our radius by 0.38 and we get our 5.32 inches. Radians are the angle measurement that people in calculus and people in physics use a lot. And you'll get much more work with it in Common Core Algebra 2 and even more work with it if you take pre-calculus and calculus eventually. So for right now, we just want you to get this idea that what radians are is the ratio of an arc length to a radius, and that gives you an indication of how much rotation you've made around some kind of a circle. All right? Just a different way of measuring rotation. So let's wrap up. In today's lesson, you saw one of the most uniquely new topics that you'll see in Common Core geometry, the idea of measuring rotation by using arc length and radius, and specifically their ratio. Their ratio gives rise to what we call a radian, or a radian measurement of rotation. Again, easy formula to use, formula you definitely need to memorize, all right? And one that over time you'll understand more and more in the context of measuring rotations and angles in ways other than just using degrees. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.